Hi everybody. In this video we're going to finish up chapter 3 talking about bootstrap confidence intervals using percentiles. And let's get started. Alright, so what we saw in the previous video is that dot plots represent bootstrap distributions, and we estimate the value of a 95% confidence interval using the formula, right? The sample statistic plus or minus 2 times the standard error. So this is a approximation formula based on the standard error, and the standard error really only works if we have a bell-shaped symmetric distribution. But we can use percentiles to find exact values of a 95% confidence interval. So this is a different technique. We're not using the formula. We'll be instead counting dots. So here is a bootstrap distribution for the mean budget in millions of dollars for Hollywood movies using samples of size 100. So this is what a bootstrap distribution using percentiles would look like. And as you can see, this is all done in StatKey. So the 95% confidence interval, it actually shows up here in the middle. And then over here, these are proportions of the number of dots contained in each tail. And the way this works is you generate a dot plot. Here I did 1,000 samples just to make the arithmetic easy. And if we're doing a 95% confidence interval, we would just select, using StatKey or by hand, you could technically count this by hand, we select the middle 95% of the dots. And the way this works is, because we're bootstrapping, we're using our original sample as an approximation of the population. So if we had access to the population, then this would be a sampling distribution, and the middle 95% of the dots would be within, 2 standard errors of the population parameter. But because this is based on the original sample, and the original sample is centered at the original sample statistic, this tells us, this 95% of the dots tells us that if our sample does represent the original population in some way, then 95% of these dots should generate confidence intervals that contain the parameter. So this is sort of what we were talking about in section 3.1 and a little bit in section 3.2. So this is the process that we use. Again, this is not a sampling distribution, but the idea is that it is a stand-in for the sampling distribution. And so this confidence interval, this tells us that 95% of the dots in this distribution are contained in this interval. Therefore, if we take the standard error and scoot that width around, whatever the size of the standard error is, and scoot it around, building confidence intervals out of each of these dots, these middle 95% would contain the actual value of the parameter. So it turns out we know what the parameter is here, but this works even if we don't know what the parameter is. And so we're interested in the middle 95% of the dots in a distribution, then we chop off the outer 5%. So that's basically the way we do it. If you look at the picture, StatKey just counts the middle, in this case 950 dots. Anything on the outside is turned red, it just gets chopped off. So the interval is the boundary between the red dot and neighboring black dot on the left, and red dot and neighboring black dot on the right. And so 2.5% of our dots are on the far left of the graph, so the left endpoint is the 2.5 percentile, right? So if you forgot what a percentile is, you might want to go back and study that. It was on your first exam, so hopefully you know what it is. 2.5% are on the far right of the graph, so the right endpoint is the 97.5 percentile. So a 95% confidence interval contains the bootstrap statistics located between the 2.5% and 97.5 percentile. And that's shown in the picture. So let's go back to the graph again. Right? So this is saying 2.5% of the dots are on the left side. So this is the 2.5 percentile. This is saying 2.5% are on the right. So this is the 97.5 percentile because 97.5% are to the left of that boundary. So this is the boundary. This is what percent of the dots are in red. This is a boundary. This is what percent of the dots are in red. This is the percent of dots in black. And again, we use StatKey to do all of this. If you have to count dots by hand, I'll show you how to do this in this presentation, but normally we use StatKey to do everything. And so StatKey easily computes the percentiles for each of the dots, and this allows us to find a confidence interval for any confidence level, not just 95%, using any symmetric bootstrap distributions, not just bell-shaped. So this is important. To use the standard error, we're using the 95% rule. The 95% rule only works when you have symmetric bell-shaped distributions. But percentiles work even if it's not bell-shaped. It still has to be symmetric for technical reasons, but it doesn't have to be bell-shaped. All right, so let's find some confidence intervals using percentiles. So find the left and right percentile endpoint values for each of the following confidence intervals. So we just saw how to do a 95%. So let's talk about how to do a 90%, 98, and 99. So we're going to do part A and B for each of these intervals. So let's start with 90%. So what are the left and right percentile endpoint values? Well, a 90% confidence interval chops off 10% of the dots, but on both sides. So that's 5% on each side, right? So that's here. Chop off 5% on the left, 5% on the right. On the right, you do 100% minus because it's the 95th percentile. If our bootstrap distribution contains values for 200 bootstrap samples, indicate how many we chop off at each end for each confidence level given. So let's say we have 200 dots and we're chopping off 5% on each end. Well, 5% of 200 is 10. So we're chopping 10 dots off of the left side and 10 dots off of the right side, right? So you just do again, I don't want you guys to do anything in your head unless you're comfortable doing math in your head. Just use a calculator. 5% of 200 is 0.05 times 200, it's 10. So we chop 10 dots off each end. So the way this works, if we're finding a 90% confidence interval with 200 bootstrap samples, StatKey will count in 10 dots, chop those off, and at those boundaries will be the indication for your confidence interval. So what about a 98% confidence interval? So 98% confidence, that's pretty confident, chop 1% off of each end. So it'll be the 1 percentile on the left and the 99 percentile on the right. So 1%, and then how many dots do we chop off if there's 200? Well, 1% of 200 is 2 dots chopped off. So we chop 2 dots off of each side, and at the boundary, we draw our confidence interval. And last one, 99% confidence. That's pretty confident. So that's a 0.5 percentile on the left, 99.5 percentile on the right, and 0.5% of 200 is 1 dot. Chop 1 dot off each end. So here's all the answers. Make sure that you guys can do this arithmetic. You have some stuff like this on the homework. The main part where this comes into play is on an exam. I can give you a dot plot and you need to count dots by hand. This tells you how many dots to chop off. So look at the confidence level, chop the same percentage of dots off each side, indicate the percentile, and then on the left side, you just do the calculation. So here, this is the first percentile on the left. 1% of 200 is 0.01 times 200 is 2. So we're chopping 2 dots off each end. So before we go any farther, I do want to point something out. There are some sort of tricky problems on the homework that have to do with this. In order to keep this video remotely short at all, I'm going to let you guys figure that out, but I'm going to tell you what happens. You still need to figure out the percentiles first. But instead of counting dots, you will be given a chart with the percentiles listed. Just pick the pick the percentile values that correspond to the percentiles. So if you're doing a 90% confidence interval, you'll be given a list of values, pick the 5th percentile and the 95th, and there'll be some numbers, and that's your answer. It's just those two numbers. So it's the same thing we're doing here, but it's a separate type of problem. Just watch out for those problems. But you still have to do part A. It's the same as this problem, part A of these problems. But part B, you're not counting dots, you're selecting from a list. All right, use percentiles in the Bootstrap distribution to find the 99% and 90% confidence intervals for the population mean number of ants on a peanut butter sandwich. So here's our Bootstrap distribution with ants on a sandwich from the previous section. So let's start with a 99% confidence interval. So we look at this and we say, how do we find a 99% confidence interval? Well, if we go back to the previous problem, we know that if there's 200 dots, we're going to chop 1 dot off each end. But here there's 1,000 dots, so we have to go through and figure out the new arithmetic. So the left is still the 0.5 percentile for a 99% confidence interval. And 0.5 times 1,000 is 0.005 times 1,000 is 5. So we're going to chop 5 dots off each end. So all you have to do, because on a test I don't want you to use StatKey, it's going to take too long. What we'll do on a test is I'll just give you a dot plot and you just count by hand. So count 5 dots off each side. 1, 2, 3, 4, 5. So our left endpoint is going to be right around here somewhere, right around 22.8, 23, something like that. And then over here, 1, 2, 3, 4, 5. Our right endpoint is going to be right around 47 somewhere. If this is a test question, it'll be multiple choice. Just pick the closest numbers. I'll show you how to do the StatKey at the end of the video again, like we did before. So here's your 99% confidence interval. And you can see that the numbers that StatKey comes up with are the same ones we got by hand, right? 22.8 and 46 point, well, if you round 46.8, right? Right around 47. So close to 23, close to 47. If this is a test question, it'll be whole numbers. So what you do is you go into StatKey, you generate the distribution, and it's all given here on the instructions, but I'm just going to tell you what you do. You don't mess with this two-tail, right tail, left tail right now. We'll do that later. You just leave this as two-tail. You just click on this number in the middle and change it to your confidence level. As soon as you do that, the two numbers at the bottom will be your confidence interval. Now notice, this is a wider interval because all we've seen so far is a 95% confidence interval. 95% confidence interval captures the middle 95%, and it's 2 standard errors. This is a lot wider, we can see, because the confidence interval captures 99% of the Bootstrap statistics. So it's actually very wide. What about let's do part B. What about the 90% confidence interval? Well, go back here, 90% confidence interval. So the left side is the 5th percentile. So that's going to be 5% times 1,000. We're doing 1,000 now in this example. So 0.05 times 1,000 is 50. So to do 90% confidence, we chop 50 dots off of each side. So just count 1, 2, 3, 4. I'm kidding. We're not going to count 50. Let StatKey do the work, right? And you can see that a 90% confidence interval is now much narrower because it only captures 90% of the Bootstrap statistics. Everything else is the same, right? To do it, you just click the center here, and then it'll show you the confidence interval. So yes, StatKey is very fast, but remember, in order to generate these things, you have to use a data set that's either built into StatKey or you have to type it in by hand. So for the ants on a sandwich, easy to type in by hand, but on a test, I can give you much more complicated data sets. You don't have to generate these on your own. And in order to do it by yourself in StatKey, it might take you an hour to type the stuff in. Some of these data sets are pretty big. So on a test, you will have to do something similar to this. If you're going to be counting dots on a test, it'll look more like this one, where you're only counting 1, 2, 5, 10 dots or something. You won't have to count 50 dots. So a higher confidence level tells us that the interval is wider. For the sandwich ants bootstrap distribution, different confidence levels give us different sizes of confidence intervals. So here's all of our ants on a sandwich ones. So a 90% confidence interval is 26 to 42.06. 95 is a little bit wider, 98 is a little bit wider, 99 is a little bit wider. And higher confidence means more bootstrap statistics are captured and the interval is wider. So that's easy to remember, right? More confidence means a wider interval because the confidence level tells you how many bootstrap statistics are captured. So why settle for less than 100% confidence? Why don't we just take that interval as wide as it can go? And the reason is that we might be 100% sure that the population mean number of ants on sandwiches is between 0 and 100 ants. But is that interval of any practical use? So if you're trying to learn something about ants, you'd really rather have a narrow range of values because it gives you information, right? Again, this is kind of a silly example with ants on a sandwich, but you can see how this applies to serious things. If we're studying the unemployment rate, you don't want a 100% chance that the unemployment rate is between 0% and 20% unemployment. That doesn't tell you anything. So we need to sort of settle on a confidence level that gives us information, but we also want to be confident that it truly does capture the population parameter. And that's why we get the 2 bullets. So we need to balance a reasonable chance of capturing the parameter of interest with the need to narrow in on where the parameter might be. And that's why we commonly use confidence levels like 90, 95, or 99%, depending on the trade-off we're willing to make between a precise narrow interval and a good chance that it succeeds. So a lot of statistics is really just based on standardization. You could do your own study and you could say it's a 93.7% confidence interval, but what does that mean? We use standardized confidence levels so that different studies who are comparing, let's say, different samples, but they're studying the same effect, if they use the same confidence level, you can compare the results to each other. So a lot of this is based on standardization. And a lot of it is also based on sort of what people expect to see. So in experimental science, or even psychology, sociology, business, marketing, any of that stuff, all these numbers are very common. 95% is by far the most common, but these other ones are common as well. And it's just because it gives us a benchmark that we can use to evaluate studies in the future. So the procedures for finding bootstrap confidence intervals are quite flexible and can be applied in a wide variety of different situations and with many different parameters. As long as we can construct a reasonable bootstrap distribution, we can use it to estimate a confidence interval. When the sample statistic is x bar, the procedure for generating bootstrap statistics is the same as examples 2 and 3 in the section 3.3 PowerPoints. So this is the ants on a sandwich, right? Whenever you have x bar, the idea is that you take your original sample, write the quantitative values on pieces of paper, throw them in a hat. It's sort of that. It's you're randomly selecting from the original sample quantitatively with replacement. When the sample statistic is p hat, the procedure for generating bootstrap statistics is the same as for C. So that was the one with the compassionate rats, where you just put x's for categorical variables, x's or just leave it blank, and then you count everything up the same way. For other sample statistics, there are other methods of generating bootstrap distributions. So let's see those now. Information on a sample of 362 college students is collected. 27 of the 193 males in the sample smoke, while 16 of the 169 females in the sample smoke. Find the best estimate for the difference in the population proportion of smokers using male proportion minus female. Use proper notation. And then find a 99% confidence interval for the difference in population proportions. Round your answers to 3 decimal places, use 1,000 samples. So I took this one from the homework. I don't know if this is exactly a homework problem, but it's the kind of problem you'll see on the homework, and it's something you could see on a test. All right, so here we need to figure out what's the population parameter. So you can see that the parameter is a difference in population proportions. So go back to that chart. Again, if you're not sure where it is, there's a reference to it right here. You're going to need this to do the homework. There's 5 parameters. Keep that list handy. So the difference in proportion, the parameter is P1 minus P2. Here we're talking about males and females, and we're going to use male proportion minus female proportion. So P1 minus P2 becomes PM minus PF. Just give them little letter names so you remember it's males minus females. So the best estimate is our sample statistic. So here you don't have to list the parameter, you have to list the sample statistic. So the best estimate for PM minus PF is P hat M minus P hat F, right? And so you just plug everything in, right? So the best estimate for the parameter is our sample statistic. So 27 out of 193 males smoke minus 16 over 169. So try that on your calculator right now. Make sure you get this number. So this is the original sample statistic. Notice it's close to the mean of the bootstrap distribution, but not exactly the same. Use this number for the center of your confidence interval. All right, for part B, find a 99% confidence interval. All right, so here's our bootstrap distribution. We want to find a 99% confidence interval. So how many dots do we chop off of each side? Pause the video and think about it if you're not sure. So a 99% confidence interval is a 0.5 percentile on the left, 99.5 percentile on the right. 0.5% times 1,000 is 0.005 times 1,000 is 5. We're going to chop 5 dots off each side. 1, 2, 3, 4, 5. So our left endpoint's going to be right about here. Right about negative 0.038. I'm just estimating here. StatKey will do the work for us, of course. 1, 2, 3, 4, 5. But on a test, estimating is fine. So here's 5 dots. Now we want to kind of split the difference here. So it's going to be about 0.135 or so. All right, and then just chop off 5 dots on either side. So this tells us that we're 99% sure that the difference in smoking rates between male and female college students is between negative 0.041 and 0.134. So based on the bootstrap confidence interval at the bottom, right? Do you guys see it down there? Make sure everybody sees it. What can we conclude, if anything, about the differences in the smoking rates of male and female college students? So this is a follow-up question, right? So the confidence interval tells us where the parameter is likely to be. So we're 99% sure that the difference in the proportions is between these two numbers. So you have lots of ways to approach a problem like this. So here's one way, if you're new to this sort of thinking, here's one way to approach it. Any number in this interval is considered a reasonable value for the parameter. So if we're taking the proportion of male smokers minus the proportion of females, that number could be negative, right? These dots are all negative. In fact, a whole bunch of the dots are negative, right? That means it's reasonable that females smoke more than males because this is a negative number. We're subtracting PM minus PF. If you get a negative number, that means PF is bigger than PM. That means more females are smokers. So it's reasonable to conclude that more females are smokers. But there's a whole bunch of positive numbers in this interval, right? Anything to the right of, like, right about here is telling us that there are more males who are smokers because these differences are all positive. So if it's reasonable or plausible that females could smoke more and it's plausible that males could smoke more, then we can't really conclude anything. And that's what I put in the notes here. So what I have here in the notes is the other way to approach it, a more direct approach. So we're 99% confident the difference between the proportions is between those two numbers, so I said that. If there is truly no difference in the population proportions, then the difference should be 0. So is it reasonable that there's no difference? Well, 0 is in this confidence interval. Therefore, it's reasonable that there's no difference. It's a believable value for the parameter. And if it's believable that it's no difference, then we can't conclude that either gender smokes more, right? So it is believable that there's no difference, and so we cannot conclude a difference exists. So we cannot conclude that males smoke more. And if you're not sure why that's true, pause the video and go back and watch all of the Chapter 3 stuff again, because the whole purpose of Chapter 3 is to learn about the parameter and draw conclusions from what we've learned about the parameter. So whenever you have like a conjectured value for the parameter, like I think there's no difference, it's believable there's no difference based on the confidence interval. Now let's go back and double check something real fast. Some of you might be thinking, but wait a second, in the sample more males smoke. So why can't I conclude that more males smoke because in the sample? So there's only one answer to that question. We've talked about it a bunch of times, and that's sampling variability. Every sample is different. So if we use this sample as a stand-in for the population, repeatedly sampling with replacement gives us a large range of values. There's lots of variability in this stand-in population. And that sampling variability causes uncertainty when making conclusions. And that uncertainty manifests itself as the width of the confidence interval. It's what we call a margin of error in section 3.1. So make sure that when we get to this sort of thing, where you have the confidence interval, you have the confidence level, you know the parameter, and then you have to do these follow-up, evaluative, is that the word? Evaluation type conclusions. You have to be able to follow through with that as well. So if the number is not in the interval, then it's not reasonable. And if the number is in the interval, whatever number you're looking for is in the interval, then it is reasonable. So there's lots of ways to handle the interpretation of this. You can either say, well, there's both negative and positive numbers in the interval, so it's reasonable that females smoke more and males smoke more, therefore I can't conclude anything. That's good. Or you could say, well, if the difference is zero is in the interval, so it's reasonable that there's no difference. That's also fine as well. You will always get the same answer using either approach if the interval has negative and positive values. Now, if this interval had all positive values, then that would tell us that males do smoke more. If it had all negative values, that would tell us that females do smoke more, with 99% confidence. All right, so a larger sample results in a narrower interval. So a large sample is more representative of the population than a small sample. So its bootstrap statistics are closer on average to the true value of the population parameter. So let's stop there for a second. We haven't really talked a ton about why large samples are preferred, but I think you can start to see it now. What we've talked about in the class so far is that representative samples are preferred. But large samples are also preferred because there's less variability and we get a narrower interval, which gives us more information. So large samples causes decreased variability among bootstrap statistics. And this decreased variability gives us a smaller confidence interval. And a smaller confidence interval is always preferred as long as it's unbiased, your sample. A smaller confidence interval is always preferred. So here's two bootstrap distributions that I made in StatKey. And what I did is I took samples of size 100 with p-hat 0.2. Okay, so again, let's say you take a sample of size 100 and 20% of that sample has some characteristic. And you build a confidence interval, you would get the confidence interval of 0.120 to 0.280. That's a pretty wide interval, right? 0.120 to 0.280. That's a big range of sample statistics, right, for where the parameter would be. But if we take a sample of size 1000 with p-hat equals 0.2, this is a much narrower interval. Now these look the same size, but it's how StatKey scales everything. There's nothing I can do about that. But just look at the numbers, right? This interval goes from 0.120 to 0.280. That's a difference of 0.16. This one goes from 0.176 to 0.225. That's a difference of around 0.05. So this interval is 3 times narrower by getting a sample that's about 10 times larger. And that is roughly true. Every time your sample size goes up by a factor of 10, the interval gets smaller by around a factor of 3. And this is one of the reasons, and big election coming up, don't know if you guys are paying attention, but it's one of the reasons that when sampling is done, especially for exit polls, on election day, many of you will be plastered to the TV watching that, and you're going to see exit poll data. And what you're going to see is a lot of these exit polls are right around size 1,000. The reason that pollsters like to get samples of around a size of 1,000 is because it narrows the confidence interval enough to get good information. But if you were to go out and take another sample of size 1,000, let's say you just combine them into size 2,000, the interval doesn't really squish that much. It's sort of a sweet spot where the amount of work you have to put into getting a new sample pays off in a narrower interval, but any more effort you put into getting a larger sample, after about 1,000, it doesn't really pay off as much. So it's kind of a little, pro-sampling thing that you might see, and it's interesting. So for most of you, that'll be happening. You'll be plastered to your TV in about 4 weeks. Unless you're watching this video much later, then it'll be about 2 weeks. But at the time of making this video, it's about 4 weeks away. So there you go. Smaller sample, wider interval, larger sample, narrower interval. That's why larger samples are preferred. And last thing, bootstrap caution. You should always look at the plot of the bootstrap distribution. If a plot is poorly behaved, you should not have much confidence in the intervals it produces. So this is a bad bootstrap distribution. You should not use this. It should be symmetric and bell-shaped to use the 95% rule, and to use percentiles, it needs to just be symmetric. This is clearly not symmetric. You would never want to use this bootstrap distribution to learn anything about the population. All right, that's the end of chapter 3. So the next video, we will start chapter 4. And if you have any questions, let me know. And here's some extra practice for you guys to work on. If you have any questions, post everything or just email me. And that's it for today. Thanks a lot. See you next video. Bye-bye.